Welcome to the lecture on logarithmic decrement and free vibration under Coulomb damping. So we have already discussed the viscous damping case, and we discussed the over damping, critical damping and under damping. And in case of under damping, we find the response, that is x equal to x0 by root 1 minus zeta square exponential e power minus zeta omega nt sine root 1 minus zeta square omega nt plus here phi 2 is the phase. So and all the three responses we can compare on in the figure shown here. So we can see here we have this overdamped system zeta greater than 1, and we can see that okay, through all the initial conditions they start and it is reaching to the equilibrium or 0 for this amount of time. Then the critical damping zeta equal to 1, and this is reaching to 0 here, and we can see both are aperiodic motion, they don't do any oscillations, and we see that the critical damping is faster than the over damping. As we said that when we increase damping, the motion becomes slower, and critical damping is the least amount of damping that will make the system to reach to 0 or equilibrium. Now comes to the under damping system. So here is the under damping system. This is undamped system, zeta equal to 0 means there is no damping, so system is following the harmonic motion, and we have the under damped zeta less than 1, and we see that this system is the amplitude is going to decay with time. Now we come to discuss logarithmic decrement, that is relevant to the underdamped system. And a logarithmic decrement is it shows the rate of decay in an underdamped system, because underdamped system has oscillations that decay with time in the exponential manner. So logarithmic decrement, it is the ratio of the two successive amplitudes on natural log. So we say delta equal to ln x1 by x2, where x1 is the first amplitude and x2 is the next amplitude. So we can find out, let's say this is our system. So let's say this is A and this is B, XA, XB, the amplitude here. So because our amplitude is given as x0 by root 1 minus zeta square into e power minus zeta omega nt. So our amplitude is given like this. Now if we say xa, that is at time t equal to ta, and this is time t equal to tb, this is time. So x0 by root 1 minus zeta square e power minus zeta omega nta, and similarly xb equal to x0 by root 1 minus zeta square e power minus zeta omega ntb. So they are xa and xb, they are two consecutive amplitudes of the underdamped system motion. So we got xa and xb. Now we put xa by xb equal to, so this will be cancelled out, we will have exponential minus zeta omega n ta minus zeta omega n tb. So this is equal to e power zeta omega n Ta plus zeta omega n Tb. So here we can write e power zeta omega n Tb minus Ta. E power zeta omega n Tb minus Ta, this is Tb minus Ta, and this is nothing but the time period, because this is the time between two peaks. And what is the time period? We can see the time period is coming from this, because this is the omega, we call it omega d, that is omega d equal to root 1 minus zeta square omega n. So this is called damped natural frequency, damped natural frequency. When zeta equal to 0, omega d equal to omega n. So the system will vibrate with this frequency when we have a damping zeta, while the undamped system was vibrating with its own natural frequency, that was omega n. So omega d is root. Here we can write also omega d by omega n square plus zeta square equal to 1. So this is showing some ellipse, and we can plot this omega d by omega n here, and this is zeta. So this is showing an ellipse. So here one. So omega d, now here we can write Tb minus Ta, that is one time period. So it is 2 pi upon omega d, and equal to e power zeta omega n into 2 pi upon omega d is root 1 minus zeta square into omega n. So omega n cancel out. We find e power 2 pi zeta upon root 1 minus zeta square. Now we take the natural log ln xa by xp equal to 2 pi zeta upon root 1 minus zeta square. So here we see that this logarithmic decrement is depending nothing but only on the damping factor zeta. When we have a zeta much less than 1, so we can write this as delta equal to ln xa by xp equal to 2 pi zeta. So this is a approximate relation for the logarithmic decrement. Okay. Now we can also write delta equal to ln x0 by x1 or ln x1 by x2 or ln xn minus 1 by xn, because delta is the log of ratio of any two successive amplitudes. So it could be between x0 and x1 or x1 and x2 or xn minus 1. Now we do like we add these terms. So we add, so this is n terms, so it is n into delta, and when we add they will come into multiplication. So x0 by x1 into x1 by x2 into xn minus 1 by xn. So all these intermediate terms will cancel out, and we will get ln x0 by xn. So here delta equal to 1 by n ln x0 by xn. So this is another expression for the logarithmic decrement. So now here we complete the viscous damping, free vibration under viscous damping. Now we start the another type of damping and free vibration of a system that has the Coulomb damping. So we already discussed the Coulomb damping as a damping due to friction between the two surfaces, and there is the dry friction and coefficient of friction mu is there, and due to this coefficient of friction and due to the movement, relative movement between the two bodies, there is this kind of damping. So we have now this system. So we represent this system. So we have a system. Let's say this is our spring and this is our mass. This mass is moving on a surface that has a coefficient of friction mu. So this is mk, and here it is moving in this direction, let's assume, and there is the friction coefficient mu between the two surfaces. On the, it is moving on horizontal surface, so there is a coefficient of friction mu between the horizontal surface and the block M. Now because the direction of the frictional force depends on the relative velocity, so in half cycle the mass will move from left to right, and another half cycle it will move from right to left. So we will have two cases of this movement. So let's say this is the mass. So mass moving from left to right. So we have this mass, and it is moving from left to right. So it is moving this is the direction of x dot, and this is x and x double dot. So in this direction we assume x and x double dot as positive. So when it is moving, we will have the spring force kx, and because it is moving this side, so the friction force will be working in this direction. So we will have a friction force here F, that is equal to mu times n, and n is the reaction, and here W is the weight and n is the reaction. Here W equal to m times g. Similarly, so we can write equation of motion. So this is a free body diagram. Now we write mx double dot equal to the forces. So x double dot direction is this, and force minus kx and minus f. So we have mx double dot plus kx plus f equal to 0. Now we can have this, we can readjust these terms. So x double dot plus so mx double dot plus k x plus f by k equal to 0. So we can write x double dot plus k by m x plus f by k equal to 0. Now we assume another axis y equal to x plus f by k. So y dot equal to x dot and y double dot equal to x double dot. Now we put these terms here and we change the coordinate. So y double dot, we can write x double dot equal to y double dot plus k by m, and here x plus f by k is y, so here it is y equal to 0. So this is nothing but showing a differential equation showing similar to the undamped free vibration. And so from here we see that the system is vibrating with the natural frequency omega n equal to root k by m. Okay. So in this case the mass will oscillate with the natural frequency, that is omega n equal to root k by m, but it will oscillate not about x equal to 0, but it will oscillate about y equal to 0. So y equal to 0 means x plus f by k equal to 0, or x equal to minus f by k. So it will oscillate about this line rather than x equal to 0. Now we take another case. The second case is when mass is moving from right to left. So here mass is moving from right to left. So we can make the free body. So this is mass and it is moving in this direction. So this is x dot. However, x is this and x double dot, we assume this direction positive, and so a spring force will be working here, because mass is still stretched to this direction, to this side, but moving towards the left side. So kx, the spring force, this time the friction force F will work in this direction, and here will be W and here the N. Now again we write the equation of motion. So here m x double dot equal to minus kx plus F. So here mx double dot plus kx minus F equal to 0. So this is the equation of motion of this system for this cycle, because in the half cycle the system, when the system is moving from left to right, it will follow this equation. When it is moving from right to left, it will follow this equation. Now again we do like mx double dot plus kx minus f by k equal to 0, and x double dot plus k by m x minus f by k equal to 0. So again we assume y equal to x minus f by k here, and y dot equal to x dot and y double dot equal to x double dot. Okay, so d square y by dt square equal to d square x by dt square. Now we will put these values here. So we will have in y coordinate y double dot plus k by m into y equal to 0. From here we find that the natural frequency omega n is root k by m, but the system is vibrating about y equal to 0, that is x minus f by k equal to 0, or x equal to plus f by k. Now what is this is this system. Now we can plot and see the response of the system, although if we want to see the response of this differential equation, so here the response of the differential equation, this one will be x equal to a1 sin omega nt plus a2 cos omega nt and minus f by k, while for equation, this is for equation 1, for equation 2, x equal to a3 sin omega n t plus a4 cos omega n t plus f by k. So now if we want to see the response of this system, so we can plot it. For this, let's assume some initial conditions. So x equal to x0 at t equal to 0. So for such initial conditions, we will start. So it means that we have this mass, say equilibrium position, and we have pushed it, this mass here. So we pushed it with x0, and then we release it. So it will start moving from right to left. So it is moving from right to left, and then in the next cycle it will move left to right. Okay. So when we have pulled it with x0 and leaving it, it is moving right to left. So here this is x0. So and this is x. So it is moving So this system here at x0 when t equal to 0, this is time, and till here, because here is the one cycle completed, and so it is tau equal to 2 pi upon omega n. And this is pi upon omega n. So this is half cycle. Half cycle, this system is moving. So this system is in this cycle doing SHM about, because this in this part it is moving right to left. So here we have the equation right to left, and it is moving about x equal to f by k, or x minus f by k equal to 0. So this is x minus f by k equal to 0 line. So this is the line for this cycle. So SHM about x equal to f by k. So in this half cycle it will vibrate about this axis. In the next half cycle, when it is moving, so here it is moving right to left. Now in this cycle till here, it will do SHM about x equal to minus f by k, because here it is moving left to right. So left to right, when it is moving, it will oscillate about x equal to minus f by k, or x plus f by k equal to 0. So this is the line here. So this is a line x plus f by k equal to 0. So this is this line, and so in this it will vibrate about this axis. So this response we can of this system having Coulomb damping, we can see also from this curve. Now we want to know that what is the oscillations, rate of decay, because we want to know that what is the kind of decay here, because although the amplitude is going to decrease, but how much? So this information we want to know. So for this, let's we say this is point A, this is point B, this is point C, point D, and point E. So it starts its motion at A, then passing through B, C, D, and E. So this is the half cycle. So we are interested to know the what is the decay in one decay of the amplitude in one cycle. This is what we want to know. And how we can know this? Because we have the response, we can see here the response. Now we can see that when we have this system K and Mx, and the system is vibrating, there is a constant friction force F, that is F equal to mu times N, and N equal to W, so mu times mg. Here all these things are constant, because mu is constant, m is constant, g. So our force is constant. So our mass is moving against a constant force. So it is doing some work against this constant force F, and in doing this force the system's energy is dissipated, and system's energy is in terms of potential energy in the spring or kinetic. This potential energy of the system, so we have at A we have a potential energy half K XA square. When the system is reaching to point C, it has potential energy half K XC square. Now the change in potential energy will be used to do the work against the friction force. So change in potential energy is this, half kx square minus half kx square, and this is friction force is F, and the net movement of this system is, so this is XA and this is XC, so XA plus XC, so total this is the movement of the system. Now we can write half K, so XA square minus XC square equal to F XA plus XC. So here we can write half K XA plus XC and XA minus XC equal to F XA plus XC. So XA plus XC, this will cancel out, and so we will get XA minus XC equal to 2F by K. So we see that the amplitude, there is the decay in the amplitude from A to C, and that decay XA minus XC equal to constant 2F by K, because F is constant and K is the stiffness of the spring, that is constant. So it is a constant quantity. So this is what we calculated for the half cycle, because from A to C it is half cycle. Similarly, for this half cycle we will find that XC minus XE equal to 2F by K. so let us say this is equation 1 and this is equation 2. Now we add this, so we will have xa minus xe equal to 4f by k. So here we see that from A to E there is a reduction in the amplitude 4f by k, a constant quantity. So here if we have this and this is this, so we have this quantity, that is 4f by k, and so this is constant, so this relation is linear. Similarly here this relation will be coming as linear, and same here, so we will have a linear relation. So this is a straight line. So we see that in case of Coulomb damping, the reduction in the amplitude, the two consecutive amplitude is 4f by k, that is a constant quantity, and the envelope that is passing through the maxima of this amplitude maxima is a straight line. If we compare with respect to the viscous underdamped viscous damping case, where the envelope was a exponential curve, so the reduction envelope was, the amplitude was reducing in an exponential way, and there the rate of decay was defined in terms of logarithmic decrement, and logarithmic decrement we defined, that was the ratio of the two consecutive amplitudes and taking the natural log of that. But here we can directly define the difference between the two amplitude xa minus xe, that is equal to 4f by k. And another important point is that in case of viscous damping, the vibration was occurring about the x equal to 0, but here in the half cycle it is occurring about x minus f by k equal to 0. In the next half cycle it is occurring about x plus f by k equal to 0. Here the frequency of vibration is the same as the undamped vibration, undamped natural frequency. So here the system is vibrating with the omega n, that is the natural frequency of the system, omega n equal to root k by m. In case of viscous damping, the system was vibrating with not omega n but a changed frequency, that was omega d, the damped natural frequency was defined omega d, that was equal to omega n root 1 minus zeta square. So there are the differences between the two the physics of the two dampings, and we understand basically the two things we were interested, the frequency of vibration and the rate of decay, and both things we have discussed for viscous damping as well as the Coulomb damping. So thank you for your attention for this lecture, and see you in the next lecture. Thank you.